Welcome back, knowledge seekers. Ready to dive deep. Today we're tackling xLSTM.
Hmm.
You know those enhanced LSTMs?
Yeah.
You sent us some seriously heavy-duty research on this. And to be honest, even I was a little intimidated at
It
first.
is dense stuff, I'll give you that. But that's what we do here, right? Break it down, make it make sense, especially for folks who really want to get under the hood, the
See,
nuts and bolts.
exactly.
Yeah,
So full disclosure, this one's for the machine learning experts out there. But hey, if you're just curious about AI, stick around. You might learn something cool along the way. Now, before we get lost in the xLSTM world, the research starts with a refresher on good old LSTMs. You know, constant error carousel, the gates, the whole 9 yards. Could you give us a quick recap?
sure. Think of an LSTM like a conveyor belt,
Right.
but it has a special memory. Information's flowing along, and the LSTM is deciding what to keep, what to chuck, what to pass along using those gates. Input, output, forget. The constant error carousel, that's the key. It helps LSTMs avoid that vanishing gradient problem, which used to be a real headache for recurrent neural networks.
Right. And the papers point out LSTMs were basically the rock stars for things like text generation, until those attention-grabbing transformers came along in 2017. But LSTMs still have some limitations, and that's where xLSTM comes in to save the day.
That's the idea. The research actually highlights three main limitations. First, LSTMs can have trouble revising their storage decisions. Imagine you're trying to find the most similar vector to a reference vector in a long sequence. An LSTM might grab onto an earlier vector that's not as similar and then fail to update its choice, even if a better match shows up later.
So it's like holding onto an outdated map even though you've got GPS telling you there's a faster route.
Exactly. Second, LSTMs have limited storage capacity. They squeeze all this information into single values called scalar cell states. And you can see how that could create a bottleneck when you're dealing with complex data, especially if you're trying to predict rare events or tokens.
It's like trying to pack for a month-long trip using only a tiny suitcase. Something's got to get left behind.
Perfect analogy. And finally, LSTMs aren't the best multitaskers. They process information step by step, which can slow them down compared to models that can juggle multiple tasks at once.
Okay, so LSTMs can be a bit rigid, limited space, prefer to work one thing at a time. Enter xLSTM stage, right? Ready to take on these challenges.
That's right. Now, the research presents xLSTM not as a single model, but as a whole family of enhancements. Two main members of the family are sLSTM and mLSTM. Each one tackles those LSTM limitations in its own way.
A family affair. I like it. So what makes each of these family members special?
Well, both sLSTM and mLSTM share a secret weapon, exponential gating. This allows them to revise those storage decisions way more effectively than classic LSTMs.
No more clinging to those outdated maps. But how does exponential gating work? What's the secret sauce?
Instead of using the typical sigmoid function to control those gates, xLSTM uses an exponential function, especially for the input gate, and sometimes the forget gate. This gives xLSTM much finer control over how information is stored and discarded.
Okay, I get it. But I'm picturing those exponential graphs shooting up to infinity. How do they keep things from exploding?
They've got some clever stabilization techniques to prevent those values from overflowing. Basically, they normalize the values to keep them in check.
So it's like a dimmer switch with a built-in safety feature. Nice. Now, what about the differences between sLSTM and mLSTM?
sLSTM keeps the scalar memory structure of the classic LSTM, but it introduces something called new memory mixing. This allows for more sophisticated interaction between those memory cells within each head.
So it's like organizing that overstuffed suitcase with compartments and dividers to make better use of the space.
Exactly. And sLSTM also uses multiple heads, each with its own set of memory cells and internal mixing, further boosting its information processing power.
Got it. What about mLSTM? What's its approach?
mLSTM goes big. It scales up to a matrix memory. Instead of a single scalar cell state, it uses a whole matrix, and a special update rule called the covariance update rule. This gives it a much larger storage capacity.
Wow, we've gone from a suitcase to a walk-in closet.
And another key difference, mLSTM is fully parallelizable. Unlike sLSTM, which still processes information sequentially, mLSTM can handle multiple computations at the same time.
So mLSTM embraces multitasking, making it much faster and more efficient.
Exactly. The research actually draws a parallel to bidirectional associative memories, or BAMs. BAMs are known for storing and retrieving pairs of vectors really efficiently, which is similar to how mLSTM uses key-value pairs for retrieval and association.
That's fascinating. So we've got sLSTM with its refined memory mixing and mLSTM with its massive matrix memory and parallel processing. But how did these fit into the overall xLSTM architecture?
That's where residual blocks come in. Both sLSTM and mLSTM are integrated into these blocks, which are then stacked to form the foundation of the xLSTM architecture.
Like building a complex structure with specialized Lego bricks.
You got it. The research really emphasizes the modularity of this design. You can stack as many xLSTM blocks as you need depending on how complex the task is.
So it's flexible and adaptable. Now I'm curious about the practical implications. How does xLSTM stack up in terms of memory and speed, especially compared to those popular transformers?
Great question. One of the big takeaways is that xLSTM has a linear computation and constant memory complexity when it comes to sequence length. Transformers, on the other hand, have quadratic memory complexity, meaning the memory they need grows much faster as the sequence gets longer.
So for really long sequences like analyzing an entire book, xLSTM has a significant advantage in terms of memory efficiency.
Absolutely. Now, for speed, mLSTM generally has the edge because of its parallel nature. Even though it uses a larger matrix memory, sLSTM with its sequential processing can be a bit slower, but they've developed optimized implementations to keep it competitive.
So they put a lot of effort into optimizing both versions for different use cases. Now the research goes on to test xLSTM on a bunch of tasks. What kind of challenges did they throw at it?
They started with some synthetic tasks, specifically formal language tasks, to see how well xLSTM could generalize and handle different levels of grammatical complexity. One example is the mod arithmetic task, where the model has to calculate the results of arithmetic operations within a sequence.
So it's like testing the model's ability to understand basic math rules within a language context.
Exactly. And they found xLSTM IST these tasks, even when tested on longer sequences than it was trained on.
Pretty impressive. But synthetic tasks are one thing. How does xLSTM perform on real-world data?
They tested that too. They used a benchmark called the Multi-Query Associative Recall task, or MQAR. This task evaluates how well a model can store and retrieve information from a long sequence. Imagine a sequence with pairs of keys and values. The model has to learn to fetch the right value when given the corresponding key, even if they're far apart in the sequence.
So it's like testing the model's long-term memory and its ability to access specific information quickly. How did xLSTM do?
It actually beat a lot of other models, including some of the latest transformer and RNN variants. The results suggest that xLSTM's enhanced memory mechanisms are really good at handling these complex associative recall tasks.
That's encouraging. Now, beyond these specific tasks, did they test xLSTM on any broader benchmarks? Something like the long-range arena, maybe?
You read my mind. The long-range arena is a benchmark suite that includes tasks like document retrieval, image classification, and this challenging task called listops, which involves understanding and executing sequences of math operations on lists.
Sounds like a decathlon for machine learning models, testing their skills across different disciplines. How did xLSTM perform in this intellectual competition?
It did remarkably well, actually. It showed strong performance across all the tasks in the long-range arena, which suggests that it's not just good at specialized benchmarks, it can handle the complexity and diversity of real-world data.
That's fantastic. But these days, the ultimate test for any language model seems to be how well it performs as a large language model.
Yep.
Did they put xLSTM through that test as well?
Absolutely. They devoted a whole section of the research to evaluating xLSTM as a large language model. They trained it on the massive Slimpajama dataset, which has a whopping 300 billion tokens.
Now, we're talking serious data. What were the key findings from these large-scale language modeling experiments? Did xLSTM live up to the hype?
It did. They found xLSTM could handle much longer sequences than it was trained on while still maintaining low perplexity, which is a measure of how well the model predicts the next word in a sequence. They even compared xLSTM to other big names like Llama Mamba and RWKV4.
Don't leave us hanging.
xLSTM actually outperformed them in terms of perplexity on the validation set. It also excelled on downstream tasks that measure common sense reasoning, showing that it's not just good at predicting words. It can actually understand and reason about the text it processes.
Wow, so xLSTM is holding its own against the giants in the large language model world. It's really impressive. Now, before we get lost in the world of benchmarks and comparisons, I want to circle back to the architecture and those formulas we promised to unpack. I'm particularly curious about how sLSTM works.
Okay, let's take a closer look at the formulas behind sLSTM, especially those exponential gates and the new memory mixing mechanism.
Perfect. Lead the way.
Okay, so let's jump into these formulas. The research gets pretty hardcore here, so get ready. It all starts with equation 8. This is the one that describes how sLSTM updates its cell state, the heart of its memory.
It does look kind of familiar, like the classic LSTM cell state update. We've got the forget gate, the input gate, the new cell input, all doing their thing.
You got it. But here's where sLSTM takes a detour. Look at equation 12. The input gate here isn't using the usual sigmoid function. Instead, it's using an exponential function applied to a mix of the input, the previous hidden state, and a bias term.
So that's the exponential gating we've been hearing about. It's like giving the input gate a much finer level of control over the information flow. But won't using an exponential function make those values go crazy?
You're right to be concerned. That's where those stabilization techniques come in equations 15, 16, and 17. They introduce the stabilizer state. It's represented by m sub t, and it basically normalizes the input and forget gates. Keeps those exponential values from causing any overflows.
So like a pressure release valve,
Yeah.
keeping the system from blowing up from all that exponential power. Pretty clever.
Yeah.
And what about that new memory mixing you mentioned? How does that fit into all of this?
That's another brilliant part of sLSTM. Traditional LSTMs often use multiple memory cells and then mix their outputs using recurrent connections. Well, sLSTM takes this a step further. It introduces multiple heads. Each head has its own set of memory cells and its own internal mixing mechanism. And this internal mixing within each head is also influenced by the exponential gating, adding another layer of complexity and control.
It's like having a team of specialists, each with their own area of expertise. And they have this way of communicating and sharing information with each other. So it's not just about having more memory, it's about using that memory in a smarter, more dynamic way.
Exactly. The formulas in the research lay it all out. You can see how this intricate dance of information happens within sLSTM.
This is fascinating stuff. Okay, so we've unpacked the sLSTM side of things. Now let's switch gears and talk about mLSTM, the one with the matrix memory. What are the key formulas and concepts we need to understand to unlock its secrets?
mLSTM takes a page from bidirectional associative memories, or BAMs. These BAMs are known for their ability to store and retrieve pairs of vectors. If you look at equation 18, you'll see the covariance update rule. This is the core of mLSTM's matrix memory. It shows how the matrix denoted as C sub t is updated based on a key value pair. The key is a vector k sub t, and the value is a vector v sub t.
So it's like creating a massive lookup table where each key is linked to a specific piece of information.
Precisely. And when we need to retrieve information, we use a query vector q sub t plus tau to search this matrix memory. The research actually highlights that this covariance update rule is optimal for retrieving binary vectors in terms of signal-to-noise ratio, which gives you a sense of how efficient mLSTM's memory mechanism is.
It's like having a super efficient search engine built right into the model. That's amazing. Now, one of the things that really impressed me about mLSTM is its parallel processing capability. How does that happen at the mathematical level? What's the magic behind the curtain?
The research actually provides detailed formulas for both the forward and backward passes in a parallelized form. Basically, mLSTM can process an entire sequence at the same time, rather than going step by step like traditional LSTMs.
So instead of reading a book page by page, mLSTM can absorb the whole book in one go.
Perfect analogy. This parallel processing is a game changer, especially when you're working with long sequences. It speeds up both training and inference significantly.
Absolutely. Now, before we wrap up this deep dive into the formulas, I want to touch on something the research mentioned about memory complexity. They emphasize that xLSTM has a constant memory complexity with respect to sequence length, unlike transformers, which have a quadratic memory complexity. Why is this difference so important?
It's a critical point, especially as we're moving towards larger and larger language models and dealing with longer and longer sequences. With transformers, the memory needed to process a sequence grows much faster as the sequence length increases. It's like the difference between stacking blocks in a straight line and building a pyramid where each layer needs way more blocks.
So for really long sequences, like processing a huge data set or a massive code base, xLSTM's constant memory complexity gives it a major advantage.
Exactly. It makes xLSTM much more scalable and practical for real-world applications where memory resources are often limited.
This is eye-opening stuff. It seems like xLSTM is tackling some of the fundamental limitations we're facing with current language models. Now, I know we've covered a lot, but is there anything else we should highlight about the architecture or the formulas before we move on? Any hidden gems we should unearth?
I think we've hit the main points. We talked about exponential gating, the stabilization techniques, the new memory mixing in sLSTM, the covariance update rule, and parallel processing in mLSTM, and of course that crucial difference in memory complexity. The research papers go into a lot more detail, but I think we've captured the essence of how xLSTM works.
Fantastic. I feel like I've gained a much deeper understanding of xLSTM, both conceptually and mathematically. Now, before we wrap up our conversation, I want to pose a question to our listeners. The research hints that xLSTM has potential beyond just language modeling. They mention applications in areas like reinforcement learning, time series prediction, and even modeling physical systems. What other possibilities do you see for this powerful family of models?
That's a great question to think about. xLSTM's versatility is really impressive. Its ability to handle those long sequences, its enhanced memory, and its efficiency make it a promising candidate for all sorts of tasks. I'm really excited to see how researchers and developers will use its strengths to solve new and challenging problems.
Me too. It feels like we're just scratching the surface of what xLSTM can do. Well, on that note of anticipation and excitement for the future of machine learning, let's bring this deep dive to a close. But before we say goodbye, I want to encourage everyone listening to check out the research papers we've been talking about. Dive into the details, explore the formulas, and see what sparks your own curiosity. Until next time, keep exploring, keep learning, and keep those brains buzzing.
Okay, so we're diving back into those sLSTM formulas. Equation 8 is our starting point. This one tells us how sLSTM updates its cell state, the core of its memory.
Yeah, it does look a bit like the classic LSTM cell state update. We see the forget gate input, gate, new cell input, all playing their roles.
You got it. But here's where sLSTM gets interesting. Look at equation 12. The input gate doesn't use that typical sigmoid function. It's using an exponential function applied to a combo of the input previous in the state and a bias term.
Right. That's the exponential gating we keep talking about, giving that input gate superfine control over the information flow. But I'm thinking, won't those values explode with an exponential function?
You're thinking ahead, which is good. That's where the stabilization comes in. Equations 15, 16, and 17 introduce a stabilizer state, m sub t. It basically normalizes those input and forget gates, prevents any overflow from those exponential values.
Like a pressure release valve. Keeps everything running smoothly even with all that exponential power.
Smart. Now what about that new memory mixing? Where does that fit in?
Another clever innovation. Traditional LSTMs use multiple memory cells and mix their outputs with recurrent connections. But sLSTM takes it further. It's got multiple heads, each with its own set of memory cells and internal mixing, and this internal mixing, it's influenced by the exponential gating too. Adds another layer of complexity and control.
It's like a team of specialists, each with their own expertise, and they can share information with each other. So it's not just more memory, it's using that memory more strategically.
Exactly. The formulas in the research really show this intricate dance of information within sLSTM. This is mind-blowing stuff. They've really taken LSTM memory to a whole new level. Okay, let's shift gears to mLSTM and that matrix memory. I'm especially interested in that covariance update rule.
Equation 18, that's the one. It describes the covariance update rule, which is central to how mLSTM stores information in its matrix memory. Think of it like building a huge searchable database. Each key is connected to a specific piece of info represented by a vector.
So instead of one value for memory, mLSTM uses a whole matrix to store and retrieve information.
Exactly. And to get specific info, you use a query vector to search that matrix memory. The research even says this covariance update rule is optimal for retrieving binary vectors. Super efficient.
Like having a super fast search engine built right in. That's impressive. Now, one of the things that stood out to me was mLSTM's parallel processing. How does that work mathematically?
The research gives detailed formulas for both the forward and backward passes in a parallelized form. Basically, mLSTM can process an entire sequence all at once, not step by step like traditional LSTMs.
So instead of reading a book page by page, it reads the whole thing at once.
Exactly. That parallel processing is a game changer, especially with long sequences. It speeds up training and inference big time.
Absolutely. Now, before we wrap up this formula deep dive, I want to touch on that memory complexity thing. The research said xLSTM has constant memory complexity with respect to sequence length. Unlike transformers, which have quadratic memory complexity. Why is that so important?
It's crucial, especially as we're going towards larger language models and longer sequences. With transformers, the memory needed grows way faster as the sequence gets longer. Think of it like stacking blocks linearly versus building a pyramid. Each layer needs way more blocks.
So for really long sequences like huge data sets, xLSTM's constant memory complexity is a huge advantage.
Exactly. Makes it much more scalable and practical for real-world stuff where memory is limited.
This has been really insightful.
Got
I
it.
feel like I've got a much better grasp on how xLSTM works both conceptually and mathematically.
Glad to hear. It's been a fun ride exploring the intricacies of sLSTM and mLSTM and how they push the boundaries of what LSTMs can do.
And for our listeners, if you want to really get into the nitty-gritty, check out the research papers. We'll link them in the show notes. They're full of details, formulas, visuals to satisfy your curiosity.
And remember, this is just the start. xLSTM is still young and evolving. Lots of potential in various fields. I'm excited to see what the future holds for these
Me
models.
too. It feels like we're just scratching the surface of what xLSTM can do.
Well,
On that note of anticipation and excitement for the future of machine learning, we'll wrap up this deep dive. Until next time, keep exploring, keep learning, and keep those brains buzzing.